Okay, so let's continue. So last time we mentioned that this link cluster theorem helps us to simplify this perturbed expansions of this Green's function, and we only need to consider the connected diagrams. And as a result, we have this lesson that if you really want to calculate this total Green's function, the full Green's function, and you can use the Feynman diagrams to diagrammatically sum up all these connected diagrams. And for example, if you consider a two-particle interaction like Coulomb-like interaction, so we could draw the Feynman diagrams order by order, starting from the free fermion propagators or free particle Green's functions, G0, which is the zeroth order, and the first non-trivial order that is linear in this interaction strength, U or V, is given by these two diagrams that we already plotted last time, right? But of course, in this linear order in interaction strengths, we have other disconnected diagrams. But those disconnect diagrams we can throw away. Okay, so we don't care about this disconnect diagram. So up to leading non-trivial order in interaction strengths, these two are the only diagrams that we can focus on. So, but if you keep doing this perturbed expansion, then you will find that at one order higher, say second order in V, you will get many, many more diagrams that need to be summed over. Okay, for example, this two balloons and a stream of two balloons and a self-energy connected to the balloon, and you could have all sort of different orientation of this bubble and the self-energy. So this could be, the balloon could be on the right part of the self-energy or the left part, and you could have a self-energy within the self-energy like this, or you have this crossing diagram like this, and you have two self-energy arranged like this, or you have a big bubble with the two strings attached to a propagator, or you have this, I don't know what this shape is, and so on and so forth. So how many diagrams are there? 10. Okay, so even at second order in potential, and you get 10 diagrams, then you know that this is not end of story, and you could keep expanding this Green's function up to third order, and I don't know how to count this and how to draw these diagrams. Of course I know, but I don't bother writing them down. So you can imagine that this number of diagrams really explodes. Okay, so it's really out of control very soon. So what can we do? So even if we apply this link cluster theorem to simplify this diagram to restrict itself to the connected diagram, then still the diagrams will be out of control very soon. As a result, we need to really continue with this analysis and find a way to sum up the complete subsets of these diagrams. Okay, so this is very important. We cannot sum up all these diagrams listed here. Okay, because as you know that even in the second order in V, there are 10 diagrams. Okay, and there's all sort of different combinations of this basic unit, and we are losing of control in third order and fourth order and so on. So it is very not practical really to think about summing up all diagrams. You don't even think about this because it is impossible. This is mission impossible. However, if we only sum up the complete subsets of these diagrams up to nth order, infinite order, and this is possible. For example, if I only care about the balloon, and I can sum up single balloon, the two balloons, and three balloons in the string, and I can also find the corresponding diagrams of the balloon, first order and second order. And you could keep tracing this balloon up to nth order, infinite number of order. Okay, so that is possible. And we could also sum up a subset of this diagram, for example, the self-energy of the electron, and you could find this in the first order, and also you can find it many like this in the second order, but you only care about this non-crossing diagrams like this, and so on and so forth, and these will be doable. So you will need to sum up only complete set of subsets. Complete refers to the fact that you sum of all this diagram, like this balloon, up to nth order. N goes to infinity, and in that sense, we really sum up a complete kind of diagrams, but this diagram is only the subset of all the possible diagrams that are listed here. So you sum up a complete subset. So, of course, it is not the full story because you don't sum up the complete sets of diagrams. I only sum up the complete subset of diagrams. Okay, so you can also sum up this self-energy diagrams, but you don't count this crossing diagram, so-called non-crossing approximation, like this. Okay, so there are many controlled approximation that is available in the literature that allows us to really simplify this calculation to restrict ourselves only to summing up a complete subsets of the diagram. Of course, when we really throw away all these other diagrams like this, and our results are not accurate, okay, because there are many contributions that we sort away. However, it is a systematic way of summing up these diagrams, a subset of diagrams, up to nth order. Otherwise, there's no way that you can sum up all the diagrams to nth order. It's very difficult to sum up the diagram up to second order, let alone nth order. So it is a reasonable approximation. But of course, we need to justify the diagrams that we throw away. So the justification of throwing away all the other diagrams not listed here is precisely this many different analytical or numerical approaches that allows us to justify, called the large N approximation. So the N refers to the number of, say, flavors, or the non-crossing approximation, and so on and so forth. So under such assumptions, we could justify that the terms that the diagrams that throw away are not important. For example, if the diagrams that are listed here is the leading term in the n goes to infinity limit. Suppose the number of flavors of this particle goes to infinity or very large value, then all these diagrams that are thrown away are not important. And of course, you could justify this non-crossing approximation by saying that all the crossing diagrams are not important because you could count this kind of powers in your controlled parameter. So we will come back to this non-crossing approximation later, but this is just to say that there is a way, approximately, available to sum up a subset of these diagrams to nth order. So, but you may wonder which one is better. So I only sum up a subsets, but I sum those diagrams up to infinity ordering interaction. Is it really more accurate than I simply just sum up a complete set of diagrams, but only limited to second order? Okay, so it is a trade-off. So you may wonder which one is better. So if I sum up all this 1 plus 2 plus 10 diagrams only up to second order, but I forget about all the rest of the diagrams from the third order up to infinite order. And this is kind of a non-crossing approximation, or this summing up the complete subset of diagrams, another approach which allows us to sum up only a subset. But by doing so, I consider how many diagrams are there. Infinite number of diagrams, right? So there are infinite number of diagrams in this approach, but I only sum up a complete subset of diagrams. But the number of diagrams is actually infinity. Okay? So the first approach, that we sum up a complete set of, not complete, but a complete in the sense that up to certain order. Say, if I can control all the diagrams up to second order, and I sum up all the diagrams, just a 13 diagram, right? So instead of summing up only 13 diagrams, I sum up infinite number of diagrams, but I only choose a particular type of diagrams that I sum up. Okay, so this is a trade-off. Of course, both approaches are not exact. Of course, nobody could solve this, sum up this Feynman diagram up to infinite order 100%. So we need to find a compromise, a kind of a reasonable approximation, which could actually give us the best result we can get. Okay, so the second approach is what I just mentioned. It is the best we can have. The best in the sense that this is much better than this first approach, of course. Well, if you can imagine a clever way to organize all these diagrams in a systematic way so that you could include more diagrams, be my guest. You could try, but this is the thing that we know up to now, right? So, and this is the best we can do. Depending on different topics and materials that you study, this could be varied. Okay, so the diagrams that you need to sum over are different, whether this is a spin system or electronic system or superconductor or whatever. So, but again, we could always find a way to only sum up this specific type of diagrams up to infinite order. Okay, so let's take a short break. When we come back, we will continue along this direction, and I will summarize this result up to second order.
Professor, excuse me. So I think some people maybe already do combine these two strategies. I mean, some kill second order and above third order just to find the subset summation is possible.
Well, so I mean, you can consider different kind of subsets. Okay, so of course there are many known results in the literature. Okay, but I'm saying that it is not possible to sum up all diagrams to all order.
Okay. But second order still can do it.
Yes, second order is almost at the boundary of our capability. And third order is probably, I have seen some calculations, I don't know, 100 pages in high energy particle physics, for example. So, and this plus minus sign, factor of 2 and factor of pi is really untractable. You know what I mean, right? Okay, so you always guarantee that you will make a mistake because there are so many diagrams, so complicated. Okay, is that okay? Good. Yeah, you can read Feynman on this chapter, where all these diagrams are shown there. You can try to compute up to only the first order. There are only 2 diagrams, and then you will find that it's not so easy task. And so this higher order diagrams, I can only draw this diagram, and you'll find it's really difficult to write them down in terms of these operators, like creation and destruction operator, and also to form the weak pairs and to form these G0s among all this a bunch of operators that in the product. So even if you want to make the weak pairs, weak contraction, you made mistakes. So we are in the jungle here. We're in a zoo of many particles. But of course, it's just an analogy. In many problems, these higher order contributions are not so important. So even at a lowest order, non-trivial order, say the first order, second order, I think if we simply just sum up this so-called irreducible diagrams and sum up to infinite order, and that should be enough, good enough. I mean, if you compare your results to the experiments, and in many cases, the first non-trivial order is actually good enough. So life is hard, but we shall survive. Okay, so this is the lesson. Let me repeat the Feynman rules one more time. But this time, we actually summarize all these rules, including this factor of -1 and fermion loop, and also the 1 over h bar factor. So this is for 2 particle interactions. So some of the rules are already mentioned previously, but I guess it's good just write down a complete version of this Feynman rules. Okay, so let me just repeat this procedure that we call this Feynman rules to draw Feynman diagrams. First, from all these topologically distinct connected diagrams, from this destruction and creation operators, and also from this interaction vortex. So with 2n vertices and 2 external points, where these 2 solid line plus 1 wavy lines meet at interaction vortex. So 2 solid lines and 1 wavy line, like this. Of course, you have another half. And each solid line, you associate the free Green's function, G0, alpha, beta, and the coordinates are this 4-dimensional coordinates, this 3-dimensional vector r and imaginary time tau, and alpha, beta are spin indices. So this x alpha are the coordinates of the final point, and this x prime beta are the coordinates of the initial point. Okay, so the line, the solid line is directly from the initial point to the final point, from x prime beta to x alpha, from this creation to destruction, right? Then for each wavy line, you attach interaction potential like this, and you integrate over all vortex coordinates, or the z's, and sum over all internal degrees of freedom. All right, so we have mentioned this. So number 5, you multiply a prefactor, which is minus 1 to the power of n plus f as an overall plus minus sign of this diagram, where I define this f as the number of closed fermion loops, and n is the order in this perturbed expansion. And you also multiply a factor of 1 over h bar to the power of n, so the overall, the total prefactor will be minus 1 over h bar to the power of n times minus 1 to the power of f. So this denominator h bar appears here because it's come with the perturbation. Okay, it's a perturbed expansion, and there's a minus 1. Now remember, this is e to the minus beta, right? So when you Taylor expand this exponential operator, time ordered operator, and there's a 1 over h bar appears in this expansion. Of course, it should appear. Okay. So total prefactor will be this one. Okay. So this is the thing that I didn't mention explicitly. And finally, you interpret this G0 at position vector r and tau 0 as this quantity that you take limit of tau goes to 0 plus, and but you calculate G0 r plus tau. In other words, you could calculate equal time correlator, but then you need to first calculate this finite tau Green's function, then you take this tau goes to 0 limit. Or in this 2 coordinate, you could consider this as the limit when tau prime goes to tau plus, and then you actually consider an equal time correlator, but these spatial coordinates are different, r and r prime are different. Okay, so these are just summarize of all these Feynman rules that we have discussed. So let's just check the signs. Okay, plus minus sign over here. Check. And for fermions only. As I mentioned, we could check up to second order. At the first order, we have 2 diagrams, right? So the first one carry the plus 1, but this is coming from minus 1 to the power of 2, where here n is actually 1 and f is actually 1. So f is 1 because there's a 1 fermion loop, and this is the first order, so n equals 1, so 1 plus 1 is 2, so minus 1 to the power of 2 is actually plus 1. And the second diagram is this, n is 1, f is 0, so you get the minus 1 as a prefactor. So I have done the simplest exercise, so the remaining diagrams become your homework. So please check the sign of all this diagram up to second order. So verify this plus minus sign in front of all these diagrams at second order. So again, this is just counting this number of closed fermion loops, and it's also the order of perturbation, but it is a good exercise. Okay, so let's take a short break. So suppose this is just the simplest exercise. because it is really straightforward to just follow the rule. Okay, so once we have the rules, and it's really simple just to follow the rules. But the most difficult part is just to really construct the rules, okay, or invent the rules. So, and as a result, it is always most difficult and challenging task to become the leader. And to be a follower, it is really, really not much challenge, okay? So if you don't see the road ahead of you, and it is really a challenging task. But once someone already clear the path for you, it simply just go through the path, and it's just piece of cake. Okay, so now we are able to start from the real space and time Green's function to the Fourier space. Okay, so in the following, we will try to Fourier transform this gx tau to either gx omega or gk omega. And in particular, this gk omega is relevant for this experimental observables that you can measure in the lab. Okay, so remember, when you perform experiments, it's almost like 99% of the chance that when you measure it, the data that coming from your machine are some sort of a gk omega, either real part or the imaginary part. So this gx tau are not so easy to be measured. So, but gk omega is this quantity that we need to really spend time. So let me just repeat and summarize this Matsubarra frequency when we perform this time Fourier transform to this Matsubarra domain. Remember, we have this time Fourier transform, of course imaginary time, taking us from gx1 x2 tau to gx1 x2 omega by this time Fourier transform, this e to the I omega n tau, where omega n refers to the Matsubarra frequency. And we have proved this Matsubarra frequency previously, right? So we take advantage of such a time Fourier transformation of this imaginary time Green's functions to this Matsubarra domain, and we could make progress based on this Matsubarra frequencies. So let us just make some assumptions. As I mentioned, in many different realistic materials, that this crystal structures show this translational invariance, which means that this g alpha beta is a function only the distance between these two coordinates, x1, x2. And also, there's a time translational invariant. It's also a common symmetry, which simplify this calculation in the time domain, in the imaginary time domain, by calculating this g alpha beta in terms of this difference between these two different time scale, tau 1 minus tau 2. So these two symmetries are very commonly seen in all these solid state systems. And also we take the thermodynamic limit where this volume of the system goes to infinity. And let me just move it here so that this g alpha beta is given by this complete Fourier transformation. In other words, this volume, this in real space goes to infinity in the thermodynamic limit, so we are talking about infinite number of particles inside that bulk. As a result, you actually match this momentum space or your Boolean zone by infinite number of k points, so that you could simply just perform this integral over your momentum, and this three-dimensional momentum integral involves infinite number of momentum points, is equivalent to this very large number of particles inside this bulk, where this volume, of course the system volume is not infinity. Oftentimes this material that we are interested in is really, really small, tiny. But why do we still consider this volume to become infinity, and we call this thermodynamic limits? Well, the underlying reason is because the number of particles goes to infinity. Remember, even very tiny piece of metal contains how many electrons? 10 to the 23rd, that many electrons or atoms. When the number of particles become almost infinity, and effectively we could just consider this volume to be infinity. So the volume becomes infinity is actually reflecting the fact that the number of particles is actually infinity. So we are not talking about the whole universe where this volume is infinity. So even this tiny little bit material that you cannot see from your bare eyes, so contains that many, almost infinite number of particles. So effectively, this is the same as volume goes to infinity. So now we'll try the Fourier transform. So one more thing, this Fourier transformation in the imaginary time previously is actually continuous integration, but since its Matsubarra frequencies are discrete points in frequency space, because n is actually integer, right? So that is omega n is always a discrete points in this frequency domain. As a result, it is the same as you simply just sum over all this discrete Matsubarra frequency. So we call this Matsubarra frequency sum or Matsubarra sum. So let me just remind you of this general form of G0 in X omega space that we mentioned earlier, which takes the same form for both fermions and bosons. And we will derive this general formulation of this Green's function. So let's just try to derive this, because this is important for later calculations. As I mentioned, when we define this G0 in the perturbed expansion, so we use this interaction picture, right? So interaction representation of this operator. So we could represent the operator in the interaction picture in terms of complete set of eigenbases. So here phi 0, J refers to the eigenfunction. J labels the eigenstates. So this is kind of a Fourier decomposition that we learn in quantum mechanics, that any wave function could be decomposed in terms of complete set of eigenfunctions, right? So here is just a second quantized version of this Fourier expansion theory in quantum mechanics. So the destruction operator in the interaction picture can be decomposed in terms of this Fourier sum. And inside the Fourier sum, you have this eigenfunctions phi 0, j, which is the basis that you expand about. And this is a time evolution operator in the interaction picture. And this aj is the destruction operator. So likewise, the psi I dagger can be expanded in terms of this aj dagger operator multiplied by this eigenfunctions and also time evolution. So remember this dagger operator in this expansion, we have this plus sign in this time evolution relative to this minus sign for this destruction operator. So with the aj and the aj dagger are simply a single particle destruction and creation operator in this eigenbasis. So now we could follow the definition of the G0 in terms of all this psi dagger at different space and time coordinate, and you expand this psi dagger in terms of all this complete eigenstates or eigenfunctions. I think this is a very good homework exercise. Derive it that you follow from the definition of the G0, and you plug in this Fourier decomposition, and you'll find that this is given by this result with this Fermi Dirac or Bose-Einstein factors like this, depending on whether tau is greater or smaller than tau prime. And you need to go back to your definition of this Green's function and plug that in, and you get maybe a dagger or a dagger A, depending on whether tau is smaller than tau prime. And then you get this 1 plus or minus nj0 in the first case when tau is larger than tau prime, and plus minus nj0 the other case. So the plus 1 refers to boson and minus for fermion as usual. Okay, so this is a very good homework just to refresh your memory and just to apply this to simple cases. And this nj0, remember, is just occupation number, right? So then you could simply just convince yourself that this is the case. So let me assign another homework. Prove this, which is this one, for both bosons and fermions. In other words, you could show that this result is actually true for both boson and fermion systems. And the way that you show this is a generic result for both boson and fermions is that you simply just plug in the Bose or Fermi statistics, and you could simplify this G0 up here, and then you sum over J. And you perform this time Fourier transformation, imaginary time, and then you simplify this. And you find that it's both in boson and fermion cases, and you end up with the same results. Okay, so you'll find some cancellations when you perform the time Fourier transformations. The cancellations happens when you perform this Fourier transformation. You find that the Fermi or Bose factors appearing here will be cancelled exactly by these factors that you perform this time Fourier transformation. So I assign this to you as a homework problem to actually convince yourself that this is a generic result which holds in both cases. So we will come back here and we will start from here and take advantage of such identity, and then we perform a further perturbative analysis for this higher order term. Okay, so let's take a short break. So you could very easily check all these calculations in our textbooks, both Flansburg and also Feynman. So these are everywhere, so you could very easily check. So this is the simplest homework exercise, the non-interacting Green's function and their Fourier transform. So next we will start from here and we introduce these two-body interactions like Coulomb interactions, and we try to Fourier transform this gx tau to gk omega and summarize this Feynman rules for this gk omega. Because when we Fourier transform, we are dealing with momentum and frequencies. So there will be momentum conservation laws and also the frequency or energy conservation involving at the interaction vortex, and we need to take care of this momentum and energy conservation. And also this prefactor are different because when we Fourier transform this Green's function to momentum and frequency space, there will be, from this momentum integration, there will be 1 over 2 pi cube, this factor, emergent, and we need to keep track of this 1 over 2 pi factor. So let's start to discuss the Feynman rules in momentum space and frequency space. So as I mentioned, we derive this non-interacting Green's function in x omega basis, right? And this general formula holds for both boson and fermion systems. So now we take a complete Fourier transformation from this gx omega to gk omega by another Fourier transformation, which is a spatial Fourier transformation. And if we take this spatial Fourier transformations, and you'll find that the general form of g alpha beta 0 with x and omega will actually reduce to this form, the simple form. Again, this simple form holds for both boson and fermion cases. And again, this is the homework. You simply just take another Fourier transformation from gx omega to gk omega, and you can start from the result of the previous homework, and you simply just take another Fourier transformation, and you see that after this Fourier sum, and those expressions reduces to this simple case. So this is our starting point that, as I mentioned, this gk omega is more useful. It's much more useful than this gx omega or gk tau. So, and we try to, again, construct the Feynman diagrams and summarize the Feynman rules in this momentum and frequency space. Okay, so let's just start this two-body interaction. So now remember, we need to Fourier transform everything to k omega space. So that includes this effective potential, this V, R tau. First, we will discuss the boson case, where omega n is even multiple frequencies. Of course, the fermion case is actually very a straightforward generalization of this bosonic case. Suppose that this potential, effective potential, when we perform the time Fourier transformation, it carries this even multiplier frequency, which is, of course, the case of the Coulomb potential, as I mentioned many times, that in the second quantized version of the Coulomb interactions, the electron actually exchanged a photon, right, with another electron. So effectively, in the Coulomb interacting electron system, it is the photon which link all these 4 electron states. And we know that photons are what? Bosons, right? So of course, gamma or photons carry even multiplier frequencies, and that's precisely what we're doing here. So we assume that this effective potential, you can consider this as a Coulomb potential. In the second quantized language, it really carries even multiplier frequencies. So let us just define this partial Fourier transformation, or it's only this R omega dependence of this potential, and we call this U. And remember this delta function that we define this v in this real, imaginary time domain. This is given by this delta tau 1 minus tau 2. So you could perform the Fourier transformation of this delta function, and this is given by this even Matsubara sum of e to the minus I omega n tau. Okay, so you plug in this delta tau back to this real space and time, the representation of this effective potential, and you perform this imaginary time Fourier transformation, and then you find that this is given by this. Remember, z1 minus z2 is given by what? U x1 minus x2 and times delta tau 1 minus tau 2. Okay, so this is the time Fourier transformation of the effective potential. So now we try to draw the Feynman diagram at the interaction vertex, which involves two electron states and the photon propagator or the bosonic propagator, like this. Remember, when we perform this time Fourier transformation on everything, so there will be e to the minus I omega n tau for this incoming particles, and there will be another Matsubara frequency which describes this frequency for this outgoing particle or electrons, e to the plus I omega n prime tau, and this is plus. And of course, these two particles exchange frequency or energies with photon or bosons, and as a result, this effective potential carry this e to the minus I omega n prime tau. So this is the time Fourier transform of the interaction vortex when this tau dependence is included in the exponential factor. So in other words, when we perform this time Fourier transformation, there's an integral over the tau, and that integral involves all this time Fourier transform of all the three different particles, like incoming particle, the outgoing particle, and also this propagator of the bosons or interaction potential. So if you collect all this tau dependent in the exponential factor, you will get this energy or frequency conservation. And this incoming particles actually carrying this omega n, this minus omega n, this Matsubara frequency, and because it is actually going to be destroyed, as a result, there's a minus sign here, because this is a destruction operator. And if you create this, and you carry this e to plus I omega double prime tau, and this boson that connect these two incoming outgoing particles carry, it is a incoming boson, so it's destroyed, and therefore this e to the minus I omega n prime times tau. So if you collect all this tau dependence in the exponentials, you'll find that this is e to the minus I times omega n plus omega n prime and minus omega n double prime. So effectively, you collect all this, you actually count energy or frequency gain or loss at that interaction vortex. So actually, you destroy the particle which carry minus omega n, but you actually create another particle carry omega n double prime, and then you actually destroy a boson which carry minus omega n prime. So you collect all this gain and loss frequencies, and this needs to be satisfied, this frequency conservation, because this is precisely this Kronecker delta function. So let me just write it here: omega n plus omega n prime minus omega n double prime. And this tells us that if this 2 omega sum omega n plus omega n prime is not equal to omega n double prime, and this summation is actually 0. If they do satisfy this frequency conservation, and the summation is actually 1. Okay, so this is so-called Kronecker delta function. So let me write it here in the standard way, so that we put a comma here in between these two different cases, which says that this is 1 if they satisfy this, and 0 not. In other words, the discrete frequencies is conserved at interaction vortex. So this is natural because, remember, in quantum mechanics, the energy is given by h bar omega. So h bar is a universal constant. So if the frequencies are conserved, so is the energy. So the quantum energy carried by all these particles should be conserved at each interaction vortex, which is what we should expect for any type of scattering event. So the energy cannot be dissipated out of no reason, right? So you cannot gain or lose energies for no reason. So if you count all these incoming and outgoing particles and their energies, and at that interaction vortex, the energy should be conserved. And this energy or frequency conservation could be very straightforwardly seen if you simply perform this time Fourier transformation at each interaction vortex. And this is a very important Feynman rules in K omega space. So let's take a short break. When we come back, we will continue talking about another important conservation, which involves momentum when you further Fourier transform this gx omega to gk omega. Any questions so far? Again, so these equation formulas are everywhere in textbooks. So it is a basic Feynman rules and Feynman diagrams. So let's continue. So I mentioned that this frequency at each interaction vortex must be conserved, so that we could arrive at this partial Fourier transformed of this Green's function like this, and then we take further Fourier transformations, which takes this g alpha beta r tau to g alpha beta k omega, and this is what we are aiming at the beginning. So then here comes the Feynman rules for this nth order contributions to the g alpha beta in this momentum space. There are n interaction vortex interaction lines and 2m plus 1 directed particle lines. So as usual, that we first draw all possible topologically distinct diagrams and connected diagrams, of course, and then we assigned direction to each particle line as usual, and we associate momentum or wave number and frequency, Matsubarra frequencies, to each line, and we conserve the frequencies and momentum at each vertex. So we will actually draw these Feynman diagrams in K omega space later. So number 3, for each particle line, the G0 propagator, as I mentioned, is given by this general form, which holds for both bosons and fermions. Then we associate this effective potential with wavy line, and we integrate over all internal variables, in this case internal momentums, and we also sum over all internal frequencies, Matsubarra frequencies. And then the spin indices from matrix product along any continuous particle line. And we can evaluate this matrix product. So we will see this later. So this is the one example. So this is a continuous line of particles. But along the line, we have a self-energy or this wavy line in between. So this spin indices are actually a result of this matrix product. So remember this delta alpha beta, which is the spin indices in the numerator right here, in this G0 alpha beta, is actually a 2x2 matrix, for example, 1, 0, 0. So when alpha equals to beta, you get 1. When alpha is not equal to beta, you get 0. So in the alpha beta basis, the spin basis, for example, this up and down, and this delta alpha beta is nothing but the matrix element of this 2x2 matrix, right? So you can construct a 2x2 matrix of any propagators like this, but then you need to really take the product of this. For example, this is alpha prime, so this is 2x2 matrix on the left, another 2x2 matrix in the middle, and the third 2x2 matrix on the right. So the final result of this self-energy in terms of the spin indices will be the product of the 3 2x2 matrices. And you take the matrix element of this resulting product of the 3 2x2 matrices as your final spin indices. So we will come back to this later. And next, the prefactor. The prefactor is a little bit complicated because we have this h bar and 2 pi factors. When we Fourier transform this Green's function to K omega space. So when you perform this time Fourier transformation, there is a 1 over beta factor in front, and when you perform this momentum sum or momentum integral, you get a 1 over 2 pi cube, this factor, in the denominator. Okay? So depending on how the powers, the orders of this perturbation, and you put this exponent n to indicate that this is the nth order contributions. Of course, the second factor is the number of Feynman loops. And so this is the complete prefactor in front of each diagram. Okay, so we have a final rule. Let me just take a short break right here. As I mentioned, this is a straightforward task to follow the rules. So you made convince yourself very easily of these rules if you go from this, say, operator forms to the diagrams and perform the Fourier transformations, and you will easily see that these are nothing but the summary of this Fourier transform of Green's function. Okay, so the final Feynman rule in K omega space is this. So when the particle line closes itself or is joined to the same interaction line, you insert the convergence factor e to the I omega n eta, where eta goes to 0 plus. So what does it mean? So when the particle line closes in itself, which means that it forms a loop, because the particle line is actually closes in itself, right? On the loop, or the particle line is joined to the same interaction line. Okay, the particle line is actually joined the same interaction line. So this is the interaction line, right? But then it joined this interaction line again. Okay, so in such case, we need to insert the convergence factor. So this factor will guarantee to make sure that the Fourier integral is convergent. So, but if you don't insert that convergence factor, you will get trouble. Okay, so we will come back to this convergence factor later. So when we perform this complex analysis or do this contour integration, so this e to the I omega n eta factor will guarantee that when we close the contour integration, and this factor guarantees that this integral is far away from origin of the other part, in addition to this, the residue part is actually vanishingly small. Okay, so this guarantees that this integral in the complex plane, which is very far away, this outer contour integral, doesn't contribute to this result. Okay, so as a result, we only collect the poles and residue when we perform this complex integral. So, and without this convergence factor, so you will see that this contour integration, for example, if we have pole here, and we need to actually go around this contour. So this factor guarantees that this integral along this infinite ranged contour should actually vanish. Okay, and you only need to care about this pole right here and the residue around that pole. Okay, so this is a very important convergence factor, and we will come back to this when we get there. Okay, so we have almost everything we need, so we can proceed to draw the Feynman diagrams of the zeros and the first order diagrams for this G alpha beta. So let me just use two ways to represent such Feynman diagrams. So these three are the simplest possible diagrams up to first order for the two particle interactions. Okay, so I label those spin indices, shown here, and this 1, 2, and 3, 4 represent all these different incoming, outgoing particle 1, particle 2, and so on. So let me just write it in this mathematical form. Okay, so let's just look at all these mathematical forms which represent these diagrams. The first one is very trivial, it's just a non-interacting. So let's look at this second and third one, which involves two space integration and two time integrations, right? 3 and 4. And remember this 3 and 4 label this particle operators in the internal degree of freedom. So variables 3 and 4 are all internal degrees of freedom. So both space and time coordinates associated with 3 and 4 should be sum over. Okay, so likewise the third diagram, you have this again internal degrees of freedom. Okay, so let's look at the second diagram, this first one of the first order term, which is what you actually have this propagator between say 1 and 3 and also 2 and 3, right? So G013 times G032, which is precisely the product of these two Green's functions, and you simply just copy all these spin indices. And then this the loop represents this G44 because this is simply just a closed Feynman loop where this incoming and outgoing particle is actually the same, going back to the same coordinate. So this will be isolated loop G044, and then all the spin indices carry through along this continuous line, so that the first spin indices for G013 is actually alpha lambda and then lambda beta, right? Alpha lambda and lambda beta. What about this loop? Well, again, this is actually a continuous line, so this should be mu mu. So you simply just make a product of these two spin, this 2x2 spin matrices, and for this, the first two G0s, and then this is again isolated 2x2 matrix. You simply take the trace, or just this diagonal elements, and this V34 represents this interaction potential, which connects this particle at 3 and this particle at 4. And there's a overall sign plus minus sign attached to the second diagram. And I don't want to assign this to your homework problem, but you can convince yourself that this is indeed the correct plus minus sign following these Feynman rules. Okay, let's look at this final diagram here. So this is the propagator from 3 to 1, and then 4 to 3, and then 2 to 4, right? So they all follow the same straight line, and in between 3 and 4 coordinates you get the interaction potential. So all these spin indices followed the straight line, alpha lambda, lambda mu, and mu beta, and then you take the matrix element of this product of the 3 2x2 matrices, and you get this final spin index. And there's no Feynman loop here. Okay, it's just a single propagating line, and then connected by this wavy line. Okay, so I guess that's it for today. Okay, so we will continue Fourier transforming this expression in the next lecture, and to the k omega space, and then we follow the Feynman rules in momentum space, and we try to evaluate this first non-trivial order of a self-energy diagram. Okay, so that's it for today, and I encourage you to read the corresponding chapter and sections either in Flansburgh or Feta Logica or other references.